So we start, this is the second lecture on eigenvalues. So the first lecture was reached the key equation, ax equal lambda x. X is the eigenvector and lambda is the eigenvalue. Now, to use that, and the good way to, after we've found, so job one is to find the eigenvalues and find the eigenvectors. Now, after we found them, what do we do with them? Well, the good way to see that is diagonalize the matrix. So the matrix is A, and I want to show, first of all, this is like the basic fact. This formula, that's the key to today's lecture. This matrix A, I put its eigenvectors in the columns of a matrix S. So S will be the eigenvector matrix, and I want to look at this magic combination S inverse AS. So can I show you what happens there? And notice, there's an S inverse. We have to be able to invert this eigenvector matrix S. So for that, we need n independent eigenvectors. So that's the case. Okay. So suppose we have n linearly independent eigenvectors of A. Put them in the columns of this matrix S. So I'm naturally going to call that the eigenvector matrix because it's got the eigenvectors in its columns. And all I want to do is show you what happens when you multiply A times S. So A times S. So this is A times the matrix with the first eigenvector in its first column, the second eigenvector in its second column, the nth eigenvector in its nth column. And how am I going to do this matrix multiplication? Well, certainly I'll do it a column at a time. And what do I get? A times the first column gives me the first column of the answer, but what is it? That's an eigenvector. A times x1 is equal to the lambda times the x1. And that lambda we'll call lambda 1, of course. So that's the first column. AX1 is the same as lambda 1 x1. AX2 is lambda 2 x2. So on along to, in the nth column, we now have lambda n xn. Looking good, but the next step is even better. So for the next step, I want to separate out those eigenvalues, those multiplying numbers, from the x's. So then I'll have just what I want. Okay, so how am I going to separate out? So that number lambda 1 is multiplying the first column. So if I want to factor it out of the first column, I better put, here is going to be x1, and that's going to multiply this matrix lambda 1 in the first entry and all zeros. You see that's going to come out right for the first column? Because we remember how we're going back to that original punchline, that if I want a number to multiply x1, then I can do it by putting x1 in that column, in the first column, and putting that number there. What am I going to have here? I'm going to have lambda 1, I'm going to have x1, x2, xn. These are going to be my columns again. I'm getting S back again. I'm getting S back again, but now what's it multiplied by? On the right, it's multiplied by, if I want lambda n xn in the last column, how do I do it? Well, the last column here will be, I'll take the last column, use these coefficients, put the lambda n down there, and it will multiply that nth column. and give me lambda nxn. There you see matrix multiplication just working for us. So I started with AS. I wrote down what it meant. A times each eigenvector. That gave me lambda times the eigenvector. And then when I peeled off the lambdas, they were on the right-hand side. So I've got S, my matrix back again, and this matrix, this diagonal matrix, the eigenvalue matrix, and I call it capital lambda, using capital letters for matrices, and lambda to prompt me that it's eigenvalues that are in there. So you see that the eigenvalues are just sitting down that diagonal. If I had a column x2 here, I would want the lambda 2 in the 2, 2 position, in the diagonal position, to multiply that x2 and give me the lambda 2 x2. That's my formula. AS is S lambda. Okay. That's you see, it's just a calculation. Now, I mentioned, and I have to mention again, this business about n independent eigenvectors. As it stands, this is all fine whether, I mean, I could be repeating the same eigenvector, but I'm no interested in that. I want to be able to invert S, and that's where this comes in. This n independent eigenvectors business comes in to tell me that that matrix is invertible. So let me, on the next board, write down what I've got. AS equals S lambda. And now I can multiply on the left by S inverse. So this is really, I can do that provided S is invertible, provided my assumption of n independent eigenvectors is satisfied. And I mentioned at the end of last time, and I'll say again, that there's a small number of matrices that don't have n independent eigenvectors. So I've got to discuss that technical point. But the most matrices that we see have n independent eigenvectors, and we can diagonalize. This is diagonalization. I could also write it, and I often will, the other way round. If I multiply on the right by S inverse, if I took this equation at the top and multiplied on the right by S inverse, I would have A left here. Now S inverse is coming from the right. So can you keep those two straight? A multiplies its eigenvectors. That's how I keep them straight. So A multiplies S. A multiplies S. And then this S inverse makes the whole thing diagonal. And this is another way of saying the same thing, putting the s's on the other side of the equation. A is S lambda S inverse. So that's the new factorization. That's the replacement for LU from elimination, or QR from Gram-Schmidt. And notice that the matrix, so it's a matrix times a diagonal matrix times the inverse of the first one. That's the combination that we'll see throughout this chapter. This combination with an S and an S inverse. Okay, can I just begin to use that? For example, what about A squared? What are the eigenvalues and eigenvectors of A squared? That's a straightforward question with an absolutely clean answer. So let me consider A squared. So I start with AX equal lambda x. And I'm headed for A squared. So let me multiply both sides by A. That's one way to get A squared on the left. So if I should write these ifs in here. If AX equals lambda x, then I multiply by A. So I get A squared x equals, well, I'm multiplying by A, so that's lambda AX. That lambda was a number, so I just put it on the left. And tell me how to make that look better. What have I got here? for if A has the eigenvalue lambda and eigenvector x, what's up with A squared? A squared x, I just multiply by A, but now for AX I'm going to substitute lambda x, so I've got lambda squared x. So from that simple calculation, my conclusion is that the eigenvalues of A squared are lambda squared. And the eigenvectors, I always think about both of those. What can I say about the eigenvalues? They're squared. What can I say about the eigenvectors? They're the same. The same x as for A. Now, let me see that also from this formula. How can I see what A squared is looking like from this formula? So that was one way to do it. Let me do it by just taking A squared from that. A squared is S lambda S inverse, that's A, times S lambda S inverse, that's A, which is, this is the beauty of eigenvalues, eigenvectors, having that S inverse and S is the identity. So I've got S lambda squared S inverse. You see what that's telling me? It's telling me the same thing that I just learned here, but in a matrix form. It's telling me that the S is the same, the eigenvectors are the same, but the eigenvalues are squared. Because this is, what's lambda squared? That's still diagonal. It's got little lambda 1 squared, lambda 2 squared, down to lambda n squared on that diagonal. Those are the eigenvalues, as we just learned, of A squared. Okay, so somehow those eigenvalues and eigenvectors are really giving you a way to see what's going on inside a matrix. Now, of course, I can continue that to the kth power, A to the kth power. If I have k of these together, do you see how S inverse S will keep canceling? In the inside, I'll have the S outside at the far left, and lambda will be in there k times, and S inverse. So what's that telling me? That's telling me that the eigenvalues of A to the kth power are the kth powers. The eigenvalues of A cubed are the cubes of the eigenvalues of A, and the eigenvectors are the same. The same. Okay. In other words, eigenvalues and eigenvectors give a great way to understand the powers of a matrix. If I take the square of a matrix, or the 100th power of a matrix, the pivots are all over the place. LU, if I multiply LU times LU times LU times LU 100 times, I've got 100 LUs. I can't do anything with them. But when I multiply S lambda S inverse by itself, when I look at the eigenvector picture 100 times, I get 100 or 99 of these guys canceling out inside, and I get A to the 100th is S lambda to the 100th S inverse. I mean, eigenvalues tell you about powers of a matrix in a way that we had no way to approach previously. For example, when do the powers of a matrix go to 0? I would call that matrix stable, maybe. So I could write down a theorem. I'll write it as a theorem, just to use that word to emphasize that here I'm getting this great fact from this eigenvalue picture. Okay, A to the k approaches 0 as k gets bigger. If what? How can I tell for a matrix A if its powers go to 0? What's somewhere inside that matrix is that information. That information is not present in the pivots. It's present in the eigenvalues. What do I need to know that if I take higher and higher powers of A, that this matrix gets smaller and smaller? Well, S and S inverse are not moving. So it's this guy that has to get small, and that's easy to understand. The requirement is all eigenvalues. So what is the requirement? The eigenvalues have to be less than 1. Now, I have to write that absolute value, because those eigenvalues could be negative, they could be complex numbers, so I'm taking the absolute value if all of those are below 1. That's, in fact, we practically see why. Let me just say that I'm operating on one assumption here, and I got to keep remembering that that assumption is still present. That assumption was that I had a full set of n independent eigenvectors. If I don't have that, then this approach is not working. So again, a pure eigenvalue approach, eigenvector approach, needs n independent eigenvectors. If we don't have n independent eigenvectors, we can't diagonalize the matrix. We can't get to a diagonal matrix. This diagonalization is only possible if S inverse makes sense. Okay, can I follow up on that point now? So you see what we get and why we want it, because we get information about the powers of a matrix just immediately from the eigenvalues. Okay, now let me follow up on this business of which matrices are diagonalizable. Sorry about that long word. So a matrix is sure. So here's the main point. A is sure to have n independent eigenvectors, and B, now here comes that word, diagonalizable. If, so we might as well get the nice case out in the open. The nice case is if all the lambdas are different. That means no repeated eigenvalues. Okay. That's the nice case. If my matrix and most matrix, if I do a random matrix in MATLAB and compute its eigenvalues, so if I took eig of rand of 10, 10, gave that MATLAB command, we'd get a random 10 by 10 matrix. We would get a list of its 10 eigenvalues, and they would be different. They would be distinct is the best word. I would have a random matrix will have 10 by 10 matrix will have 10 distinct eigenvalues, and if it does, the eigenvectors are automatically independent. So that's a nice fact. I'll refer you to the text for the proof. That A is sure to have n independent eigenvectors if the eigenvalues are different. If all eigenvalues are different. It's just if some lambdas are repeated, then I have to look more closely. If an eigenvalue is repeated, I have to check. Has it got, say it's repeated 3 times. So what's a possibility for, so here's the repeated possibility. And let me emphasize the conclusion, that if I have repeated eigenvalues, I may or may not have n independent eigenvectors. I might. This isn't a completely negative case. The identity matrix. Well, suppose I take the 10 by 10 identity matrix. What are the eigenvalues of that matrix? So let's take the easiest matrix, the identity. If I look for its eigenvalues, they're all 1s. So that eigenvalue 1 is repeated 10 times. But there's no shortage of eigenvectors for the identity matrix. In fact, every vector is an eigenvector. So I can take 10 independent vectors. Oh, well, what happens to everything? If A is the identity matrix, let's just think that one through in our head. If A is the identity matrix, then it's got plenty of eigenvectors. I choose 10 independent vectors. They're the columns of S. And what do I get from S inverse AS? I get I again, right? If A is the identity, and of course, that's the correct lambda. The matrix was already diagonal. So if the matrix is already diagonal, then the lambda is the same as the matrix. A diagonal matrix has got its eigenvalues sitting right there in front of you. Now, if it's triangular, the eigenvalues are still sitting there. But so let's take a case where it's triangular. Suppose A is like 2, 1, 2, 0. So there's a case that's going to be trouble. There's a case that's going to be trouble. First of all, what are the eigenvalues? I mean, we just, like now, if we start with a matrix, the first thing we do, practically without thinking, is compute the eigenvalues and eigenvectors. Okay, so what are the eigenvalues? You can tell me right away what they are. They're 2 and 2. Right. It's a triangular matrix. So when I do this determinant, shall I do this determinant of A minus lambda I? I'll get this 2 minus lambda, 1, 0, 2 minus lambda, right? I take that determinant, so I make those into vertical bars to mean determinant. And what's the determinant? It's 2 minus lambda squared. What are the roots? Lambda equal 2 twice. So the eigenvalues are lambda equals 2 and 2. Okay, fine. Now, the next step, find the eigenvectors. So I look for eigenvectors, and what do I find for this guy? Eigenvectors for this guy, when I subtract 2 minus the identity, so A minus 2i has zeros here, and I'm looking for the null space. What are the eigenvectors? They're the null space of A minus lambda I. The null space is only one dimensional. This is a case where I don't have enough eigenvectors. My algebraic multiplicity is 2. I would say when I count how often the eigenvalue is repeated, that's the algebraic multiplicity. That's the multiplicity. How many times is it the root of the polynomial? My polynomial is 2 minus lambda squared. It's a double root. So my algebraic multiplicity is 2. But the geometric multiplicity, which looks for vectors, looks for eigenvectors, and which means the null space of this thing. And the only eigenvector is 1, 0. That's in the null space. 0, 1 is not in the null space. The null space is only one-dimensional. So there's a matrix, this A or the original A, that are not diagonalizable. I can't find 2 independent eigenvectors. There's only one. Okay. So that's the case that that's a case that I'm not really handling. For example, when I wrote down up here that the powers went to 0 if the eigenvalues were below 1, I didn't really handle that case of repeated eigenvalues because my reasoning was based on this formula. And this formula is based on n independent eigenvectors. Okay, so just to say that. There are some matrices that we don't cover through diagonalization, but the great majority we do. Okay, and we're always okay if we have different, distinct eigenvalues. Okay, that's the typical case. Because for each eigenvalue, there's at least one eigenvector. The algebraic multiplicity here is 1 for every eigenvalue, and the geometric multiplicity is 1. There's one eigenvector, and they are independent. Okay. Okay. Now, let me come back to the important case when we're okay. The important case when we are diagonalizing. Let me look at, let me solve this equation. The equation will be I start with a given vector u0. And then my equation is that every step I multiply what I have by a. That equation ought to be simple to handle. And I'd like to be able to solve it. How would I find, if I start with a vector u0, and I multiply by a 100 times, what have I got? Well, I can certainly write down a formula for the answer. So so u1 is a u0. And u2 is, what's u2 then? u2, I get from u1 by another multiplying by a, so I've got a twice. And my formula is uk, after k steps, I've multiplied by a k times the original u0. You see what I'm doing? The next section is going to solve systems of differential equations. I'm going to have derivatives. This section is the nice one. It solves difference equations. I would call that a difference equation. It's a first order. I would call that a first order system because it only goes up one level. And it's a system because these are vectors and that's a matrix. And the solution is just that. Okay, but that's a nice formula. That's like the most compact formula I could ever get. U100 would be a to the 100th u0. But how would I actually find u100? How would I discover what u100 is? Let me show you how. Here's the idea. To really solve, shall I say, to really solve. To really solve it, I would take this initial vector, u0, and I would write it as a combination of eigenvectors. To really solve, write u0 as a combination, say, certain amount of the first eigenvector plus a certain amount of the second eigenvector plus a certain amount of the last eigenvector. Now multiply by a. You got to see the magic of eigenvectors working. Multiply by a. So a u0. is what? So A times that. A times, so what's, I can separate it out into n separate pieces, and that's the whole point. That each of those pieces is going in its own merry way. Each of those pieces is an eigenvector, and when I multiply by A, what does this piece become? So that's some amount of the first, let's suppose the eigenvectors are normalized to be unit vectors. So that says what the eigenvector is. It's, and I need some multiple of it to produce u naught. Okay. Now when I multiply by A, what do I get? I get C1, which is just a factor, times AX1, but AX1 is lambda 1 x1. When I multiply this by A, I get C2 lambda 2 x2. And here I get Cn lambda n xn. And suppose I multiply by A to the 100th power now. Can we, having done it, multiply by A, let's multiply by A to the 100th. What happens to this first term when I multiply by A to the 100th? It's got that factor lambda to the 100th. That's the key. That's what I mean by going its own merry way. It is pure eigenvector. It's exactly in a direction where multiplication by A just brings in a scalar factor lambda 1. So 100 times brings in this 100 times. 100 times lambda 2. 100 times lambda n. Actually, what are we seeing here? We're seeing this same lambda, capital lambda to the 100th, as in the diagonalization, and we're seeing the S matrix, the matrix S of eigenvectors. That's what this has got to amount to. A lambda to the 100th power times an S times this vector C that's telling us how much of each one is in the original thing. So if I had to really find the 100th power, I would take u naught, I would expand it as a combination of eigenvectors. This is really S, the eigenvector matrix, times C, the coefficient vector. And then I would immediately, by inserting these 100th powers of eigenvalues, I'd have the answer. So there must be, well, let's see. Okay. So if U100 is A to the 100th times U naught, and U naught is SC, then you see this formula is just this formula, which is the way I would actually get hold of this U100, which is, let me put it here, U100. The way I would actually get hold of that, see what the solution is after 100 steps, would be expand the initial vector into eigenvectors and let each eigenvector go its own way, multiplying by 100 by lambda at every step, and therefore by lambda to the 100th power after 100 steps. Can I do an example? So that's the formulas. Now let me take an example. I'll use the Fibonacci sequence as an example. So Fibonacci example. You remember the Fibonacci numbers? If we start with 1 and 1 as F naught, oh, I think I start with 0 maybe. Let 0 and 1 be the first one. So there's F0 and F1, the first two Fibonacci numbers. Then what's the rule for Fibonacci numbers? They're the sum. The next one is the sum of those, so it's 1. The next one is the sum of those, so it's 2. The next one is the sum of those, so it's 3. Well, it looks like 1, 2, 3, 4, 5, but somehow it's not going to do that way. The next one is 5, right. 2 and 3 makes 5. The next one is 8. The next one is 13. And the 100th Fibonacci number is what? That's my question. How could I get a formula for the 100th number? And for example, how could I answer the question, how fast are they growing? How fast are those Fibonacci numbers growing? They're certainly growing. It's not a stable case. Whatever the eigenvalues of whatever matrix it is, they're not smaller than 1. These numbers are growing. But how fast are they growing? The answer lies in the eigenvalue. So I've got to find the matrix. So let me write down the Fibonacci rule. Fk plus 2 is Fk plus 1 plus Fk. Right? Now that's not in my... I want to write that as uk plus 1 and auk. But right now, what I've got is a single equation, not a system. And it's second order. It's like having a second order differential equation with second derivative. I want to get first derivatives. Here I want to get first difference. So the way to do it is to introduce uk will be a vector. See, a small trick. Let uk be a vector, fk plus 1 and fk. So I'm going to get a 2 by 2 system, first order, instead of a scalar system, second order, by a simple trick. I'm just going to add in an equation, fk plus 1 equals fk plus 1. That will be my second equation. Then this is my system. This is my unknown. And what's my one-step equation? So now uk plus 1. So uk plus 1 is the left side. And what have I got here on the right side? I've got some matrix multiplying uk. Can you see that all right? If you can see it, then you can tell me what the matrix is. You see that I'm taking my system here. I artificially made it into a system. I artificially made the unknown into a vector. And now I'm ready to look at and see what the matrix is. So do you see the left side, uk plus 1 is fk plus 2, fk plus 1. That's just what I want. On the right side, remember, this uk here, let me for the moment put it as fk plus 1 fk. So what's the matrix? Well, that has a 1 and a 1, and that has a 1 and a 0. There's the matrix. You see that gives me the right-hand side. So there's the matrix A, and this is our friend UK. So so that simple trick changed the second order scalar problem to a first order system with two unknowns, with a matrix, and now what do I do? Well, before I even think, I find its eigenvalues and eigenvectors. So what are the eigenvalues and eigenvectors of that matrix? Let's see, first let me just think for a minute. It's 2 by 2, so this shouldn't be impossible to do. All right, let's do it. Okay, so my matrix again is 1, 1, 1, 0. It's symmetric, by the way. So what I will eventually know about symmetric matrices is that the eigenvalues will come out real. I won't get any complex numbers here. And the eigenvectors, once I get those, actually will be orthogonal. But 2 by 2, I'm more interested in what the actual numbers are. What do I know about those two numbers? Well, do you want me to find this determinant of a minus lambda I? Sure. So it's the determinant of 1 minus lambda 1, 1, 0, right? Minus lambda, yes, God. Okay. Okay. There'll be two eigenvalues. Well, tell me again what I know about the two eigenvalues before I go any further. Tell me something about these two eigenvalues. What do they add up to? Lambda 1 plus lambda 2 is the same as the trace down the diagonal of the matrix. 1 and 0 is 1. So lambda 1 plus lambda 2 should come out to be 1. And lambda 1 times lambda 2 should come out to be the determinant, which is minus 1. So I'm expecting the eigenvalues to add to 1 and to multiply to minus 1. But let's just see it happen here. If I multiply this out, I get that times that will be a lambda squared minus lambda minus 1. Good. Lambda squared minus lambda minus 1. Actually, you see compare that with the original equation that I started with. Fk plus 2 minus Fk plus 1 minus Fk is 0. The recursion that the Fibonacci number satisfy is somehow showing up directly here for the eigenvalues when we set that to 0. Okay, let's solve. Well, I would like to be able to factor that quadratic, but I'm better off to use the quadratic formula. Lambda is, let's see, minus b is 1 plus or minus the square root of b squared, which is 1, minus 4 times that, which is plus 4 over 2. So that's the square root of 5. So the eigenvalues are lambda 1 is 1/2 of 1 plus square root of 5, and lambda 2 is 1/2 of 1 minus square root of 5. And sure enough, those add up to 1, and they multiply to give minus 1. Okay, those are the two eigenvalues. What are those numbers approximately? Square root of 5, well, it's more than 2, but less than 3. It'd be nice to know these numbers. I think so that number comes out bigger than 1, right? Yeah, that's right. This number comes out bigger than 1. It's about 1.618 or something. Not exactly. And suppose it's 1.1. Just like, I think so. Then what's lambda 2? Is lambda 2 positive or negative? Negative, right? Because it's obviously negative, and I knew that so it's minus, and they add up to 1, so minus 0.618, I guess. Okay, and some more. Those are the two eigenvalues. One eigenvalue bigger than 1, one eigenvalue smaller than 1. Actually, that's a great situation to be in. Of course, the eigenvalues are different, so there's no doubt whatever. Is this matrix diagonalizable? Is this matrix diagonalizable, that original matrix A? Sure. We've got two distinct eigenvalues, and we can find the eigenvectors in a moment. But they'll be independent, will be diagonalizable, and now you can already answer my very first question. How fast are those Fibonacci numbers increasing? They're increasing, right? They're not doubling at every step. Let's look again at these numbers. 5, 8, 13. It's not obvious. The next one would be 21, 34. So to get some idea of what F100 is, can you give me any, I mean, the crucial number, so it's approximately, what's controlling the growth of these Fibonacci numbers? It's the eigenvalues. And which eigenvalue is controlling that growth? The big ones. So F100 will it be approximately some constant, C1 I guess, times this lambda 1, this 1 plus square root of 5 over 2 to the 100th power. And the 200th F, in other words, the eigenvalue, the Fibonacci numbers are growing by about that factor. You see that we've got precise information about the Fibonacci numbers out of the eigenvalue. Okay. And again, why is that true? Let me go over to this board and show what I'm doing here. The original initial value is some combination of eigenvectors, and then when we start going out the series of Fibonacci numbers, when we start multiplying by a 100 times, it says lambda 1 to the 100th. This term is the one that's taken over. I mean, that's big, like 1.6 to the 100th power. The second term is practically nothing, right? The 0.6 or minus 0.6 to the 100th power is an extremely small number. So there are only two terms because we're 2 by 2. This number is, this piece of it is there, but it's disappearing. Where this piece is there and it's growing and controlling everything. So really we're doing like problems that are evolving. We're doing dynamic. Instead of AX equal B, that's a static problem. Now we're doing dynamics. A squared, A cubed. Things are evolving in time, and the eigenvalues are the crucial numbers. Okay, I guess to complete this, I better write down the eigenvectors. So we should complete the whole process by finding the eigenvectors. Okay, well I have to, up in the corner then, I have to look at A minus lambda I. So A minus lambda I is this 1 minus lambda, 1, 1, and minus lambda. And now, can we spot an eigenvector out of that? That's for these two lambdas, this matrix is singular. I guess the eigenvector, 2 by 2 ought to be easy. So if I know that this matrix is singular, then it seems to me the eigenvector has to be lambda and 1, because that multiplication will give me the 0. And this multiplication better give me also 0. Do you see why it does? This is the minus lambda squared plus lambda plus 1. It's the thing that's 0, because these lambdas are special. There's the eigenvector. x1 is lambda 1, 1, and x2 is lambda 2, 1. I did that as a little trick that was available in the 2 by 2 case. So now I finally have to, I have to take the initial u0. So to complete this example entirely, I have to say, okay, what was u0? u0 was f1, f0. So u0, the starting vector, is f1, f0, and those were 1 and 0. So I have to use that vector. So I have to look for a multiple of the first eigenvector and the second to produce u0, the 1, 0 vector. This is what we'll find C1 and C2, and then I'm done. So let me, instead of in the last 5 seconds grinding out a formula, let me repeat the idea. It's the idea that's central. When things are evolving in time, let me come back to this board because the ideas are here. When things are evolving in time by a first-order system, starting from an original U0, the key is find the eigenvalues and eigenvectors of A. That will tell, those eigenvectors, the eigenvalues will already tell you what's happening. Is the solution blowing up? Is it going to 0? What's it doing? And then, to find out exactly a formula, you have to take your U0 and write it as a combination of eigenvectors, and then follow each eigenvector separately. And that's really what this formula, the formula for, that's what the formula for a to the k is doing. So remember that formula for a to the k is s, lambda to the k, s inverse. Okay, that's difference equations, and you just have to, so the homework will give some examples different from Fibonacci to follow through. And next time will be differential equations.